Hello, welcome everyone. It's 11 o'clock, so I think we'll all get started. Welcome everyone. My name is Sonia Pepple and I am the SLL representative for the West Midlands. We do currently have everyone muted on the call, just to limit background noise. However, we are accepting questions, so if you do have any throughout the presentation, we'll get those through, and then obviously we'll try and answer as many as we can then at the end of the presentation. If you think of any questions later on, or if there's anything obviously that brings up new things, new questions, and these can be emailed after the presentation to sll@cibse.org. And if you wouldn't mind headering your email with subject well V2 and with today's date as well, at least then we can differentiate between any other emails. So on behalf of the SLL and CIBSE West Midlands, I'd like to welcome you to the CPD, and it's all about the WELL standard requirements for electric lighting. So our speaker today is Sophie Parry, who is the Vice Chair of the Technical and Publications Committee and is also a Fellow of the Society of Light and Lighting. So I'll hand over straight over to Sophie. Thank you.
Good morning, everybody. Hi, it's Sophie Parry here, and today I'm going to talk to you about the WELL 2 standard and the requirements for electric lighting as to be found in that standard. So let me close this down. Okay. So the way the WELL 2 standard works, it's a whole building standard. It's a little bit like BREEAM or Pearl, and that you have various aspects of your project or your building that are associated with quality and the occupant experience. So you can see there that we've got these 10 concepts, and the one that we're particularly interested in is light. Which is what we're going to talk about today, but do bear in mind this is just part of WELL 2 certification. So WELL 2 is a whole building points-based system. It's based on 11 subject preconditions, which are not negotiable. That means that for each of those categories I showed you on the last slide, you have to meet the preconditions as a bare minimum to look at WELL certification. You can't just pick and choose and perhaps load all the points into one or two. So it has to be a balanced approach. There are two lighting preconditions, which I'll talk about later on. And then on top of the preconditions, we have something called optimizations, which are additional performance specification items, in this case for lighting, which would enhance the lighting installation beyond the two preconditions. And what happens here is that the preconditions and the optimizations will attract points. So as you can see on the table there, depending on which certification you're going for, you could be just doing a shell and core type project where you only need 40 points for the entry-level certificate, but most projects are either going for silver, gold or platinum. So like BREEAM, you need to work out what you're going to go for, what your performance specification is at the start of the design phase, and where those points are going to come from, so that you can actually create a design steer and a performance specification to achieve those points. So lighting's interesting. As I say, there are two preconditions, and then you've got your optimizations, which can actually create up to 14 points, although you're only allowed to carry 12 over into your certification. These points are on a scale of 1 to 100 as well, so just like BREEAM. Like all standards now and documents, there is a disclaimer inside the front cover. It doesn't just apply to lighting, it applies to the whole WELL 2 standard and certification system. I would say, as regards lighting, some of the aspects of lighting that are asked for in the optimization is still part of ongoing and developing science, particularly surrounding circadian lighting and equivalent Melanopic Lux. But we'll go into that in more detail, but just be aware that this does sit inside the front cover. So, Melanopic Lux. What exactly is Melanopic Lux? Well, if you can imagine, if our starting point for any good lighting design is actually natural light, a gift from nature rather than electric light. All electric light does is try and emulate what nature gives us. But there's some interesting things going on. So with the human eye has receptors in it which are designed, A, to pick up photopic information from natural light or indeed electric light, which is then transmitted to the brain via these green neural pathways, which allows us to interpret the images in our brain and understand what we're actually seeing in terms of form and colour and texture. But there are also other sensors in the human eye which are nothing to do with visual acuity. These sensors pick up cues from natural light and to a certain extent electric light. And these non-visual cues or non-visual acuity is used to recalibrate your body clock, usually every day, and also to suppress or allow the production of hormones. So if we look at these neural pathways here, the blue, there's various functions within the brain that apply to wellness and recalibrate your body clock each day, provided you do get some natural light, obviously. And if you think of the primeval response before we had electric light, and most of us spent up probably our days outside, or our ancestors as hunter-gatherers, what would have happened when we got up first thing in the morning? The non-visual aspect of natural light, even if it was a cloudy day, so you would have diffused daylight, would suppress the production of the melatonin hormone, which would give us a bit of a boost to start our day. So if you can imagine first thing in the morning, if you go out on a nice sunny day, then you're going to feel good about yourself, and it should set you up, unless you've got other underlying health issues, for a good productive day, which is the idea of that. However, you're going to burn energy during that day while you're out hunter-gathering or whatever you were doing in those times. So towards the end of the day, when the sun is starting to set down over the horizon and it goes from an orange down to an orangey colour, and then what happens is the orangey lower colour temperature of the sun, and it's not the colour temperature of the sun, it's actually the received light coming through the upper atmosphere that changes the colour of the sun. That's also picked up by the eyes, and it basically says, okay, we now need to start releasing this melatonin hormone, because this is going to make us relax and prepare for a good night's sleep. Okay, so this is what happens with the human eye and the human body in terms of picking up cues during the day and into the early evening from natural light. And over the last 120 years or so, whereas we started to come indoors, when we've been using electric light has allowed us to see, but it's not necessarily carried out these non-visual functions for us. And that's what Melanopic Lux is, the melanopic content of light that actually, if you like, looks after your wellness, recalibrates your body clock, suppresses or releases melatonin hormone, is the Melanopic Lux, or the non-visual effect of light. So if we just have a look at the light spectrum, let's bring it back now. This is a daylight spectrum report for Northern Europe, what we call D65, or on average 6,500 Kelvin, bearing in mind that we have a lot of cloud in Northern Europe as well. So typically we talk about 6,500 as being the average. And if this graph here shows the visual spectrum of light that we see, generally speaking, or that is available to the human eye, from about 300 nanometers up to about 900 nanometers. But within that visible spectrum of light, we've got two interesting subcomponents. So first of all, we've got this blue one here, this C lambda. This is the part of the visible light spectrum, or the light spectrum rather, that contains the melanopic lux, or the non-visual aspect of light. And then if we move over to the green peak here, the V lambda, that's called the photopic content of visual light, and that's what allows us to see objects and form. So these are the two main elements within light as we receive it, okay, that we interpret. So what does that look like? If we then take, say, an LED luminaire, And we look at the visible wavelength and the light being emitted from that luminaire. What we want to be able to do is start to come close to replicating what we get from nature. So this is an LED luminaire that's been put in a spectrometer and a similar trace obtained. And as you can see, there is a nice spike here to represent C lambda. So when we talk about blue spikes in LED lighting and people say blue spikes are dangerous, you shouldn't have blue spikes in LED, there is actually a blue spike in nature, the melanopic content. So it's not a bad thing, but what happens with some LED luminaires that are not very well engineered in terms of the LED and the phosphor is that this blue spike goes off the scale, and that gives them that horrible blue, cold tinge about them, and that's not good. So what you need to do in a good quality engineered luminaire is you need to have this C lambda peak or this melanopic peak, but you need to keep it under control. So the amplitude is where you would expect it to be, rather than just off the scale. And then as you can see, that's on the border of blue and azure. And then as we come through the light spectrum, we come up into the orange and the red. This area here, as we come up through the greens over to here, this is the part that actually allows for visual acuity. So this also needs some consideration as well. We need some red in it for richness of colour and also to bring out colours. Red is a particularly important component. And then eventually what happens is we start to leave the visible light spectrum and we go off into infrared, where you're not going to be able to see anything as a human being. So, yeah, as I said, Melanopic Lux, C lambda is a subcomponent of the visual light spectrum. Traditional designs for interior light, they only concentrate on the photopic lux level. So when you're working in programs like Relux and Dilux, you're actually looking at the photopic content or illumination levels of light. And within WELL 2, they do talk about the equivalent melanopic lux being generated by electric lights to get close to emulating what nature gives us as part of the wellness. And equivalent melanopic lux can be calculated and applied to a design. But I'll show you how that's done and how that's measured and calculated in future slides. So now we understand some of the terminology that we're going to hear about today. If you didn't already know that, let's actually have a look what it says in the WELL standard regarding electric lighting. So as I mentioned, there are two preconditions. The first one, LO1, this is light exposure and education of users. So this is more about designing your building to allow natural light into the building and take advantage of that free gift from nature. Obviously, depending on the building and the orientation, you can only do so much of that. Otherwise, you start to introduce solar gain, and the cost of air conditioning in summer tend to start to go through the roof. So we know that we can let natural light in, but it has to be controlled, and we may need solar shading to control it at certain times of the day and the year. But it is something that you design to in architecture, and that needs to be taken into account to the relevant levels, and LO1 will tell you your local standard that you're designing to meet that precondition. LO2, the other precondition, visual lighting design, this is essentially lighting design and specification to EN 12464-1, which is what we should be designing to every day in Northern Europe. We might not use this terminology every day, but that's basically where our illumination levels come from, our UGR, our uniformity, etc., etc. So we probably don't even realise we're using that sometimes when we're designing, but we do. And providing that your design meets EN 12464-1, then you meet LO2. And the interesting thing with LO1 in terms of designing with natural light, if you can't meet it, as often happens in our climate in Northern Europe, it does tell you that if you can't meet it by using natural light alone and the correct fenestration and architectural layout, then you need to compensate by going straight to LO3. Okay, which I'll come on to now. So those are the two preconditions, which is kind of what we do anyway, so there's nothing unusual there. But when we come to the optimizations, which may be specified as performance objectives for the project, and it will be on a project-by-project basis. The first one is LO3, circadian lighting. Now, this is an optimization based on delivering the equivalent 150 to 240 melanopic lux. in the vertical or cylindrical plane at about 1.4 meters for Cat A, or about at 450 millimeters above workstations, and for 4 hours. Those 4 hours are usually from 9 a.m. in the morning to 1 p.m. in the afternoon. And of course, this optimization is going to attract points as well if you do achieve it, particularly with electric lighting. And I'll show you how that's designed, because LO3 is probably one of the most common optimizations that we're seeing in performance specifications for Well 2 at the moment. The next one is LO4, glare control. Part 1 is architectural, but may include shading control, which may require automatic control via the lighting control systems. So there is an input there for lighting design as well, particularly with lighting controls, if it is mechanized shading control. And in part 2 of LO4 is the luminaires themselves, how they're actually constructed, are they fit for purpose, especially in office and education, where we're looking at how the light is emitted, looking at achieving the correct UGR reading in our model, in our design model, and also that the shielding angles are correct for the height of the luminaire based on the light intensity going out, or the candela per square meter going out. So yeah, you could achieve LO2 to a certain extent, but then you might use a luminaire that maybe not quite fit for purpose, in which case you wouldn't achieve this optimization when it came to glare control. So excuse me, just moving something around on my screen. So LO5, enhanced daylight excess. This is to do with the architects. If they start putting skylights in and atria and things like that, that may attract more points. LO6, visual balance. Mostly architectural, but supported by the timing of the light changes and levels. So what this means is that when you've got a lighting control system, if you're going to shift from one light level to another automatically, so it's part of the programming rather than a manual intervention, if you're going to start taking light levels down because you are receiving information from outside via, say, photocells that say that there's good natural light coming in the building and the electric lighting levels can be dropped, you need to drop them gradually over at least 30 minutes so that it doesn't actually spook the occupants, because if they don't know what's going on, they're likely to phone the facilities managers and tell them there's something wrong with the lighting. Can they come and fix it? When actually it's daylight linking actually doing its job. But it's a good idea to use a good quality system that allows the lowering of the electric lighting levels to take place over a fade down period of time of at least 30 minutes, so it barely becomes noticeable. It's actually the opposite. If you want to bring the lighting levels up automatically, you can do it in just a few seconds. People take comfort and security in lighting levels going up, but they do get worried when they start noticing them going down quite quickly. The other thing as well is when you're designing, particularly, say, an open plan office area and you've got notional lighting zones, you'll probably be working to either 300 or 500 lux at the actual workstation positions, but then you'll have peripheral circulation areas, maybe storage areas. You should be looking at the scale of illuminance and working down to those peripheral areas at 200 or 150 lux, for instance, rather than just some random lighting number. So again, you're going to get points for that. LO7, electric light quality. This is about colour rendering index, or TM30. We don't really use TM30 in the UK at the moment. This is something that's come out of the US. I think just one manufacturer puts both CRI and TM30 on their data sheets at the moment. But generally speaking, we still work in RA or CRI in Europe. But the interesting thing to note is if you want to achieve LO3, circadian lighting, and get your equivalent Melanopic Lux, you need to be very careful which types of luminaires you use. So typically, education and office lighting has usually been CRI 80 for the last few years. You can use CRI 80 luminaires, provided they've got an R9 content greater than 50, R9 being the red content of the emitted light. But those luminaires are actually quite difficult to find and also quite expensive to produce. So generally, the way you make your design comply is to use CRI 90 luminaires, which will give you a much better chance of actually making it all work. So I think the moral there is that if you are showing clients and architects luminaire samples very early on to try and get a fix on the luminaire schedule, make sure you show them a luminaire that is available in CRI 90. Otherwise, you might have to go back with your tail between your legs and explain that you need to do that exercise again if you can't get the design to work. That CRI 90 or CRI 80 with R9 greater than 50 is only going to apply over workstation positions. As soon as you come away from that and you've got your notional circulation or your physical corridors and your lobbies, you can go back down to CRI 80 anyway. The other aspect of LO7 is flicker. This is probably one of the most tricky ones to deal with at the moment because most of the WELL standard has been changed from the USA way of thinking to a European way of thinking for Europe, which is good. But the one area that's still a little bit tricky is is flicker. So what they actually ask for in the WELL 2 standard is that flicker should comply with the IEEE 1798 2015 standard. Now, the IEEE standard is a US standard. It's not a European standard. We don't use it in Europe. And by LED standards, it's quite an old standard now. It's 5 years old. But we can actually take the metrics from it, and there's been some other work done as well to show what's good and what's bad. So what we're actually looking for really is the flicker, the frequency should be a minimum of 90 hertz. But actually, in Europe, where we have 50 hertz mains, what will actually come out of a driver in an LED luminaire is an output with 100 hertz. Although it's DC, there will be a background of 100 hertz on that output from the driver. So we're okay there. But what we actually have to look at is what we call modulation depth, particularly on dimmable luminaires. So, and that's where the problem starts. So what you're looking for is a modulation depth of ideally 3%, but certainly no more than 5% on your luminaire driver. So it's usually quite a good quality driver to achieve those numbers. And it should hold those numbers if you then start to dim the luminaire in 10% increments all the way down to virtual off, to be honest. There is some notes on flicker going to appear in the latest version of BSEN 124611, which is up for review at the moment. It's actually been rewritten last year, and we did see the draft, and we expect to see the new BSEN standard for lighting issued either later this year or early next year, and there'll be a lot more on flicker and what's acceptable in that new standard, I'm told. Which means then it will go back to LO2. So if we're complying with LO2 in the latest version of 12461, then we should automatically be complying with LO7 as well on flicker. The final optimization is LO8, occupant control of the lit environment. So this is about using freestanding luminaires and individual lighting controls. So this does already happen. This is quite popular in some European countries, but what we do find in the UK and Ireland is that what we tend to do is we try and light everything from the ceiling. So everything has to go in the ceiling, and that's where we do our lighting from. And maybe on the odd occasion, if there's something special going on at the workstation, we might use a task light. But what we don't do, as a general rule of thumb, is design with freestanding luminaires near or adjacent to workstations or groups of workstations with just a basic overhead lighting scheme as an infill scheme. As I say, it is used in some countries, and what it does provide a better quality in offices and education in terms of the delivered lighting. And also, it usually doesn't use as much energy as a traditional ceiling-mounted scheme. The other good thing with these freestanding luminaires is that you can put individual lighting controls on the stalk of the freestanding luminaire. So if you've got one per workstation or one per two workstations, there's more granularity and respect for co-workers when adjusting the lighting control levels, which could be that dimming it down a little bit, even switching it off, maybe adjusting the color temperature. So it is used in other countries. It's just a cultural thing. We tend to do things the way we've always done in this country. We don't always try new ideas for various reasons associated with commercial and design risk. But it is worth thinking about in the future that this may be a way that we need to start to go as well. So just in conclusion then of all of these optimizations and the preconditions, a compliant lighting and controls scheme could actually contribute up to 24% of a WELL Silver certification, 20% of a WELL Gold certification, or 15% of a WELL Platinum score, which is quite interesting because it means that if lighting is going to be a big part of the WELL certification, which it usually is, then the developer and the architect will be speaking to the lighting design community much earlier than perhaps they do at the moment, because there is a lot of work to do and a lot of considerations to take into account to get that design to work. Okay, so let's just go back to this LO1 natural light contribution. What did I actually mean by that? So if we look at this image on the left, what we actually see here is a typical, could be an educational, could be an office environment, but not untypical in more modern architecture, where we've got nice fenestration, lots of good natural light coming in at certain times of the day. Yeah, quite a nice environment to work in, I would say. And I think anybody entering that space, if there was tables or desks available nearer the windows, they would probably automatically gravitate to want to sit closer to the window rather than deep into the floor plan where it might be a bit murkier. So if we take this image and we turn it into plan view, what we've actually got from a lighting engineering perspective is we will have a useful day lighting zone, which is close to the fenestration. And as we go deeper into the floor plates, especially on deep pan offices, we're going to end up with this area where the daylight doesn't really provide useful penetration in terms of doing a job of work at a workstation, and we start to rely more on electric light. So what can we do about this? So if we're going to design to LO3 and we need to get our equivalent Melanopic Lux from electric light, depending on the daylighting design and what the expert who's done the daylighting design tells us, we may be able to say that the luminaires closest to the window don't need to deliver any equivalent Melanopic Lux between 9 a.m. and 1 p.m. because this is going to be a gift from nature anyway. So these could just be standard fixed temperature luminaires in this zone. But you do need to take that information and that cue from your lighting designer or your daylighting designer, rather than just assuming you can take a rule of thumb 6 meters or 3 meters and it's just going to happen. You really do need to be sure, and you need to take advice from a daylighting engineer that that's what's going to happen and that they're going to stand by it. But as you come deeper, you're going to have your electric lighting zone where you are going to rely on these luminaires almost certainly to provide the equivalent Melanopic Lux. And to be honest, if you took the worst case scenario, perhaps a day in December, then the chances are these are all going to be luminaires that can deliver the equivalent Melanopic Lux on the basis that there might be no natural light in sort of November, December, January, February in Northern Europe. So how would we do it? So we'd use a lighting control system, and we'd have 2 modes. So mode 1, which would be 9 a.m. to 1 p.m., this would basically set the lighting up to deliver the equivalent Melanopic Lux target as LO3. Now, depending on the quality of luminaire, and also whether it's a CRI 80 or a CRI 90 luminaire, what you might find is that you don't actually have to change the illumination levels or the color temperature of the luminaires to hit your EML target. It might just work anyway in its default state at 100%. But what you might find is that during the 9 a.m. to 1 p.m. time slot, what you've actually got to do is either use the lighting control level to bring the illumination level up a little bit, so you're actually bringing the illumination of everything up to get that EML from within, or you're changing the color temperature of your luminaire, so you might be shifting from 4000K to 5000K for 4 hours, just to achieve this EML target. But once you get to 1 p.m. and you've done that, then your second mode in your lighting control systems will basically just take the design back to a photopic illumination system as per LO2, so your usual 300, 500 lux, and you're not worried about delivering your EML target. You've already done that for the day. So yeah, you're going to need a lighting control system, and you're going to need to set it up for 2 modes, and then you're going to need to model both modes as well, and particularly if you're going for LO3. Okay, so design to the WELL standard. It's likely to be an office or an educational project. You can do Cat A projects and you can do Cat B projects. If it's Cat A, you just do a general background level across the open floor plate, pending Cat B. But generally speaking, if it's Cat B and you know the positions of the workstations, then life's going to be a lot easier. But what you'll need as well, when you're selecting your luminaires, you're going to need the EML illumination derating factors for the preferred luminaire. So I'm going to show you how they're calculated or where you can get that information from. But you are going to need that information to hand. And again, I would always suggest that make sure the luminaire that you're proposing, and if you're showing samples or talking about luminaires in the early days with your client, is to either go for a CRI 80 with an R9 of 50, or ideally a CRI 90 luminaire. And you can actually achieve these designs, particularly at CRI 90, with fixed output luminaires. It doesn't have to be tunable white. But again, it might be a good idea to make sure that the luminaire that you are presenting is available in tunable white, just in case you find during the later design phases that you need to do that when you're working out what happens in mode 1 and mode 2 on your design. But remember, let's say, for instance, we're working in Dilux. So Dilux is only ever going to give us photopic results. But what we generally do is we do a Dilux plot in the usual way, and I'll show you one of those. But then we do vertical slices, which quite often we do anyway in education and office. And we look at, in that vertical slice in the Dilux plot, what's actually happening at working plane plus 450 millimeters, or at 1,400 millimeters above finished floor level for Cat A. If it's Cat A, we use a 9.3 square meter grid. If it's Cat B, then we know where the workstations are, and we can create a task area for each workstation and just concentrate on the equivalent Melanopic Lux and illumination within each workstation task area. As I said, should really calculate for nighttime conditions because of our climate in Northern Europe. But if you are going to take a daylight contribution, please make sure that that's added by the architect or the lighting designer with a specialism in daylighting engineering. Otherwise, it could go horribly wrong for you. But remember, you are working in a lighting program which provides you with photopic plots, photopic being the element of light that allows you to see, which is no good for EML, so we have to do a conversion, and I'll show you how that's done. The other thing to mention as well, we're talking a lot about the design phase here, is that the project will likely need on-site verification as per the WELL standard lighting verification method, and a revisit every 12 months to check the lighting levels and the quality of lighting, because things do move around in buildings over a period of time. So if you are doing verification then or retesting, you would probably almost certainly be measuring is in photopic using a standard light meter, and then you can derate that back to EML to check the EML levels, because melanopic light meters are very rare and very expensive. So there isn't many of those about outside laboratories. Okay, so let's just go through designing now. So go back to LO2 and BSEN 12464-1, which is our default standard for internal lighting in workplaces. So if you're working in lighting, you're probably familiar with these sorts of plots from Dilux where we look in plan view. This is a Cat B job, so we know where all the workstations are. The red lines indicate linear luminaires, and from that, the usual thing, we can get the metrics, the illumination levels, the uniformity, the UGR, etc., etc. And that's photopic, okay? That's nothing to do with equivalent melanopic lux. That's just purely photopic. And you can see over here where we've got little, where we're looking at individual workstations. We've created a task area around a workstation, and we've just pulled out the metrics for that area there. Just to give us an idea of what's actually going on over somebody's desk. So we should be familiar with that as lighting designers. That's kind of what we do every day. But then we need to go a stage further. So we talked about vertical or cylindrical illumination. And what we're thinking about here is either somebody sat at a desk or somebody stood up, or maybe two people stood up talking. And also the task area illumination, which we always do anyway. So these are the things we've got going on here. But let's have a look at this green band, because this is where our equivalent melanopic lux is going to come from. So if we take that green band and then we extract it, this is a vertical slice from the Dilux plot that I showed you on the previous screen. And we bring it down so that we are basically 450 millimeters above the workstation. So we're sort of 1200 to 1600 millimeters there. So in that zone. And these are all the individual vertical illumination points in photopic lux. So if we then take that out and say, well, where exactly is that in that previous Dilux? Here's a 3D from the previous Dilux. You can see that band of light that we're looking at in the vertical is roughly going to equate with the average adult's face or somebody stood up. So that's where the equivalent melanopic lux between 9 a.m. and 1 p.m. needs to come into play. So how do we get this EML ratio? So if you don't already have the data for the luminaire, you're going to need a laboratory with a spectrometer. So what happens is a luminaire is put into a spectrometer and measurements are taken starting at 380 nanometers up to 525, which is basically the visible light spectrum, as you can see on this graphic here. And all of this information has to be extracted and filled in on a spreadsheet. So as you can see, you're going to need a laboratory with the right equipment to do this. However, this luminaire here is a typical 4000K LED luminaire. And when you put all of this information in and you click for your results, you get a melanopic ratio, in this case 0.760, which is good because that's what we're going to need to times our photopic illumination by to get the EML content. However, that all looks a bit messy and time consuming and not available to everybody. So what you should start to see now is manufacturers are actually putting this information on data sheets. So this luminaire here, it's a CRI 90 luminaire, tunable white from 2,700 to 6,500K. You'll notice the interesting thing is that the luminous flux stays constant regardless of the color temperature. And this is an international data sheet, so please ignore the first two columns. The one we'd be interested in here is the MEER column, the melanopic. And you'll see different ratios depending on the color temperature. Okay, starting at 0.53 down at 2,700 Kelvin, which means there's not much equivalent melanopic lux at that color temperature. But when you come up to 6,500 Kelvin, then it's up to 1.06. So it's very rich in equivalent melanopic lux. But we don't tend to put 6,500K into our projects in the UK. We usually run about 4,000K, where you'll see 0.8, which is a typical derating factor. Okay, because that's kind of the preferred colour for the UK market. And as I said, in mode 1 with your lighting control system, you may have to up it because obviously the higher this ratio is, the better your number's going to be, and it depends on your luminaire. So so long as we've got this information one way or another, what we do is, if you remember this vertical slice I took, we need to take the mean average of the illumination or the photopic lux levels in that green band, and then we multiply it by the EML ratio or the MEER value to determine the EML lux levels in that band. So a typical example would be for this luminaire here, we know the average photopic is 424 lux in that band. And at 4,000K, it's actually the factor is 0.8. So if we times it by 424 by 0.8, we end up with an equivalent melanopic lux of 339 lux. Now, we only need it between 140 and 249. Most people go for 249. So we're well within there. That design is going to work. We won't even have to shift it off 4,000K because it was a CRI 90 luminaire. And that's quite an easy design to do. But you do have to remember to work between photopic and melanopic lux by using these ratios. You won't get that straight out of your lighting design program. I talked a little bit about verification before. Well project implementation states that completed projects will need verifying for design compliance. Generally what this means is there's a well certification engineer who's a generalist in all aspects of well compliance, so they're not necessarily going to be a lighting expert. So you would probably be meeting them on site when the building is complete and occupied, and they would have a list of what they needed to look at, and you would probably, as a lighter or a consultant, be expected to provide the instrumentation and demonstrate that you were hitting the numbers so that they could sign off on it, ready for the certification. And again, you can reverse engineer what I've just showed you. So if you're measuring photopics, then you can actually say this is the derating factor for the luminaires installed to get back to the EML ratio, and you can just take the maths backwards, if you like, just to show that you're actually hitting those levels. Now, if you're wondering about managing verification, it is, if you like, an extended commissioning process. If you are not familiar with the CIBSE Commissioning Code L for lighting from 2018, when it was last updated, the processes described in Commissioning Code L are very compatible with the WELL standard verification requirements. So you would be able to develop your commissioning method statement by using the templates in Commissioning Code L to work with a WELL verification project. Applications, as I said, the two main ones are office and education. I do get asked about logistics centres. We don't necessarily put lighting in, say, a windowless warehouse, because they tend to operate on a 3-shift system. And as I said at the beginning, the science is not that far advanced yet with circadian lighting that we would be comfortable actually suggesting that we went through 3 mode 1s a day to represent each shift system, or took into account the middle of the night and tried to create daylight conditions. That could cause health problems in the medium to long term. So until the science is sure on that, all I would suggest on a logistics centre is that the whole site may well have WELL certification, but the lighting in terms of LO3 should be limited perhaps just to the office and admin areas where people tend to work, perhaps 9 till 5. Same applies to data centres. Great big buildings, usually windowless, apart from around the reception. I wouldn't recommend, again, doing the full WELL lighting scheme for a data centre. What I would suggest is just think maybe about the control hub, which is usually windowless for security reasons, and the people working long shifts in there. Hospitals, the NHS is not necessarily using this at the moment, but some private hospitals are starting to see the benefit, particularly in day rooms where people sit because they can't get outside. So you can actually use circadian lightings in day rooms and rest areas. And also you'll find day rooms and rest areas in retirement homes as well. And there are examples out there in the UK where private hospitals and retirement homes are now using circadian lighting to benefit the wellness of the occupants. But yeah, just be careful on the ones of asterisk that you don't apply it with blanket coverage across a project like you might do, say, with an office building or an educational building. Let's just talk a bit about the standards and how this is aligning. So the concept of lighting for well-being is not new. It's now just being updated to incorporate the latest research and technology. There are 3 main standards that are underpinning this. So the WELL building standard is not something that's just been dreamt up for commercial gain. Certainly for lighting, it is underpinned by some pretty respectable standards. So the first one is the CIE 026/E from 2018. This is a system of metrology for optical radiation for IPRGC influence responses to light. IPRGC, those are the sensors in the eye that serve your non-visual acuity. So those are little sensors in your eyes that allow you to take information from light to recalibrate your body clock and suppress or release hormones. So they're using some big fancy words there, which I haven't used today, but basically it boils down to the same thing. The next standard is the ISO standard, WDTR2783, light and lighting. integrative lighting. Now, again, ISO have decided not to call it circadian lighting or human-centric lighting. They've decided to call it integrative lighting, which is basically the non-visual effects of lighting. And then finally, the one that it probably influences most of our day-to-day work as designers is BSEN 124641, light and lighting of workplaces, indoor workplaces. We're on the 2011 version at the moment. Last year, there was a draft proposal to update this standard, and as I say, that should be released later this year or 2021 at the very latest. And there's quite a lot of new stuff in there that also points towards wellness and circadian lighting to a degree. For us in SLL, what will happen is that once the BSEN 12464-1 is released and we've had a chance to digest it, then that will trigger a revised edition of LG7 lighting for offices. So we can't revise LG7 until at least we see this new BSEN standard. So just to conclude, there are actually three models for measuring and specifying the amount of light required to provide circadian stimulus. So the first one is the equivalent Melanopic Lux method. This was actually developed at Manchester University a while back now and has been adopted by the Well Building Standard as their protocol or method of doing this. The next one is MDEI, or Melanopic Day Light equivalent illuminance. This has come out of Germany. So it's embodied in two DIN specifications. And this is all about daylight illuminance, vertical illuminance, variable colour changing temperatures at certain times of day with 6,500 K as the reference correlated colour temperature. We don't really see specifications based on DIN standards in the UK. I've yet to see one. So that's generally happening in Germany, Switzerland and Austria at the moment. And the third one is circadian stimulus value, or CS. This has come out of the Lighting Research Centre in Albany, New York. And this is about spectrally weighted irradiance of the cornea for acute melatonin suppression. So again, a slightly different play on words, but all points to the same thing. Circadian stimulus value was an interesting one because it was originally developed for NASA for use on the International Space Station, which orbits the Earth 16 times a day. So they have 16 sunrises and sunsets over a 24-hour period, which means if you're an astronaut on the International Space Station, it starts to mess with your head after a few weeks because we're used to just having one sunrise and sunset at 24-hour intervals. So it was originally developed for that and is actually used on the International Space Station as the method of trying to control well-being. In terms of validating this, as of July 2019, there is an impartial DRE CIBSE report that has tested all three of these protocols in a building which was measured as a benchmark in East Anglia and then retrofitted with LED lighting. So it was one floor of an office block. But what the outcome of this exercise is that all three protocols are difficult to achieve in practice, but the EML or the MDEI are easier than CS to achieve. In an office or an education environment, the effect is subjective, psychological, and more real-world testing is required to fully confirm to medium to long-term benefits. This is why I said right at the beginning that the science on circadian lighting is ongoing. We have enough knowledge of circadian lighting at this point in time for it to gain traction in documents such as the WELL standard and the two DIN specifications in Germany, but these documents will be updated in the fullness of time as the science progresses and hopefully completes. But just be aware of that. The main variable in this is human beings. We all have different quality of eyesight depending on our age usually. So macular degeneration sits in, and what, say, a 50-year-old would consider a good lighting level in an office, you might find the office junior at 20 years of age is not necessarily agreeing with that. So, yeah, the big variable in all of these environments is actually the humans that use them. So everything that I've shown you today is sort of a mean average in terms of trying to satisfy most of the people most of the time. And that's my presentation for today. Thank you very much. Back to you, Sonia and Juliet, for questions.
Lovely. Thank you very much, Sophie.